Hello everyone, and welcome to today's presentation on electrostatic potential and capacitance. I'm excited to have you here as we explore these fundamental concepts in electromagnetism. On this first slide, you can see the title, and I'd like to briefly mention that we'll be covering the principles behind electrostatic potential, how capacitance is defined, and their applications. So, let's dive in and get started. Let's take a closer look at the key concepts, starting with the basic ideas behind electrostatics. We'll explore how charges interact and how potential energy plays a role in these interactions. Moving forward, we'll examine the electrostatic potential, which is essentially the work done in bringing a charge from infinity to a point in space. We'll then delve into the potential due to a system of charges, which helps us understand the combined effects of multiple charges. Next, we'll explore the relation between electric field and potential, highlighting how they are interconnected. The concept of electrostatic potential energy is fundamental. It's the energy stored in a system of charges due to their positions. We'll look at how potential energy varies at different points in an electric field and what happens when charges are placed in external fields. As we proceed, we'll cover how the potential due to a point charge behaves and extend that understanding to more complex distributions. Then, we'll examine special structures like the Van de Graaff generator and the effects of dielectrics on capacitance, which are crucial for understanding how energy is stored in capacitors. Speaking of capacitors, we'll analyze the parallel plate capacitor, including how energy is stored within it, and look at various ways to connect capacitors to modify their properties. The role of dielectric materials and polarization will also be discussed, as they significantly influence capacitance. Finally, we'll explore the energy stored in capacitors and how it relates to potential energy in external fields. Throughout this journey, we'll connect these concepts to build a comprehensive understanding of electrostatics and energy storage in electrical systems. Let's talk about some fundamental variables that are essential in understanding electrostatics. First, we have the electrostatic potential energy, which is a key concept. This energy represents the work needed to bring a charge from infinity to a specific point in an electric field without acceleration. It's important because it helps us understand how charges interact and the energy stored in these interactions. Think of it as the potential for work, much like gravitational potential energy, but for electric charges. This concept connects directly to the overall theme of electrostatics, as it explains how charges influence each other and how energy is conserved within these systems. When we analyze forces between charges, considering their potential energy gives us a clearer picture of the stability and behavior of charge configurations. So, understanding electrostatic potential energy is fundamental to grasping the bigger picture of how electric fields and forces operate in various contexts. Let's now discuss the concept of potential due to a system of charges. When we talk about potential, we're referring to the electric potential at a point in the space around charges. This potential is essentially the amount of electric potential energy per unit charge at that location. In a system with multiple charges, each charge contributes to the total potential at a point. What's important here is that the total potential is the algebraic sum of the potentials created by each individual charge. This is because electric potential is a scalar quantity, so it simply adds up without regard to direction. Understanding this helps us analyze complex charge distributions and predict how they influence the space around them. It's a fundamental step toward grasping how electric fields and potentials interact in more complicated systems. So, in summary, the potential at any point due to a system of charges is the sum of the potentials due to each charge, and this principle underpins much of our understanding of electrostatics. Let's talk about the potential due to a point charge. When we have a single point charge, the electric potential it creates depends on the distance from that charge. The key idea here is that the potential is higher closer to the charge and decreases as you move farther away. This potential is scalar, meaning it has magnitude but no direction, which makes calculations simpler. The formula for the potential at a point in space is proportional to the magnitude of the charge and inversely proportional to the distance from the charge. Specifically, the potential V at a distance r from the charge Q is given by V equals K times Q divided by R, where K is Coulomb's constant. This concept is fundamental because it helps us understand how electric fields influence space around charges. It also forms the basis for more complex systems, like multiple charges or continuous charge distributions. Understanding the potential helps us visualize how energy is stored in the electric field, which is crucial for many applications in physics and engineering. So, in essence, the potential due to a point charge is a straightforward but powerful concept that links charge, distance, and energy in the electric field. All right, let's dive into the potential due to an electric dipole. On this slide, we're focusing on how an electric dipole generates a potential in its surroundings. As you can see, the key parameters here include the dipole moment, which is represented by the symbol Q times A, where Q is the magnitude of the charge and A is the separation distance. The potential created by a dipole depends on the position relative to the dipole, specifically the distance and the angle theta between the dipole axis and the point where we're calculating the potential. It's important to understand that the potential due to a dipole decreases with distance, but its directional dependence is critical. It varies with the cosine of the angle theta. This angular dependence is what makes dipole fields unique compared to monopole fields. By grasping this concept, we see how dipoles influence their environment differently, which plays a vital role in many physical phenomena, from molecular interactions to electromagnetic applications. This understanding of potential due to an electric dipole connects directly to our overall theme of electrostatics and field interactions, highlighting the importance of dipole moments in understanding electric fields. Let's talk about equipotential surfaces. These are surfaces where the potential at every point is the same, meaning no matter where you are on that surface, the potential doesn't change. Now, an important point to remember is that for any charged configuration, the electric field is always perpendicular to these surfaces. If it weren't, there would be a component of the electric field along the surface, which would cause the potential to vary across it. This would contradict the very definition of an equipotential surface. So, in essence, the electric field must always be perpendicular to these surfaces to maintain a constant potential. This relationship is fundamental because it helps us visualize how electric fields behave around charges and how potential changes in space. Let's examine this slide, starting with the concept of delta, which represents an infinitesimal displacement. When we talk about the change in potential, or delta V, this change is measured per unit displacement normal to the equipotential surface at a given point. Essentially, this tells us how the potential varies as we move in a specific direction. Now, a key idea here is that the electric field points in the direction where the potential decreases most steeply. So, if you imagine walking along a surface where the potential remains constant, the electric field is always perpendicular to that surface and points toward the direction of the steepest decline in potential. From these observations, we can draw two important conclusions. First, the magnitude of the electric field is directly proportional to the rate at which the potential drops per unit of displacement normal to the equipotential surface. Second, the electric field vector itself points in the direction where the potential decreases most rapidly. Connecting this to the overall theme, understanding this relationship helps us see how potential and electric field are fundamentally linked, with the field essentially guiding us along the steepest potential descent. This connection is crucial for grasping how electric forces operate in various scenarios. Let's take a closer look at the potential energy of a dipole in an electric field. As you can see, the variables involved include the dipole moment Q, the electric field E, and the angle theta between them. The potential energy depends on how these factors interact. When the dipole aligns with the electric field, the potential energy reaches a minimum, meaning the system is most stable. Conversely, when the dipole is opposite to the field, the energy is at its maximum, indicating an unstable configuration. Understanding this relationship is key because it helps us grasp how dipoles behave in electric fields, which is fundamental in many applications, from molecular chemistry to electrical engineering. So, recognizing how potential energy varies with orientation gives us insight into the forces and torques acting on dipoles in different environments. All right, let's take a closer look at slide 10, which focuses on the surface charge density, denoted as sigma or sigma. This is a crucial concept because it tells us how much charge is distributed per unit area on the surface of our capacitor plates. You'll notice the slide shows positive and negative signs around sigma, indicating that one plate carries a positive charge while the other carries a negative charge. Now, moving on, we see the symbol E, which represents the electric field created between the plates. This field is directly related to the surface charge density. Higher sigma means a stronger electric field. The direction of E is from the positive to the negative plate, which makes sense because that's the direction a positive test charge would move. Next, there's the distance. Labeled as d, this is the separation between the two plates, and it's a key factor because the electric field strength depends inversely on this distance. The closer the plates are, the stronger the electric field for a given surface charge density. Finally, the area A refers to the surface area of each plate. The larger the area, the more charge the plates can hold, which directly impacts the capacitance of the device. So, tying it all together, these parameters, surface charge density, electric field, distance, and area, are fundamental in understanding how a parallel plate capacitor stores and manages electric energy. They're interconnected, and understanding their relationships helps us grasp how capacitors function in circuits and systems. Let's take a closer look at how the dielectric material influences the capacitance. As you can see, the surface charge density, denoted by sigma, varies across different regions, with both positive and negative values. This variation plays a crucial role in how the electric field, E, is established within the capacitor. The area, A, also factors into this, of course, since capacitance depends on the surface area of the plates. Now, when we introduce a dielectric between the plates, it affects the overall electric field and the potential difference. The dielectric essentially reduces the electric field for a given charge, which in turn increases the capacitance. This is because the dielectric material polarizes in response to the electric field, creating an opposing field that lowers the net field inside the capacitor. It's important to note that the parameters we're considering, like surface charge density and the electric field, are directly influenced by the dielectric's properties. The key takeaway here is that the dielectric increases the capacitance by decreasing the effective electric field, allowing the capacitor to store more charge for the same voltage. This effect is fundamental to many applications, from simple capacitors in electronic circuits to complex energy storage systems. Understanding how the dielectric modifies these parameters helps us design better, more efficient capacitors tailored to specific needs. Now, let's take a look at how capacitors can be combined to achieve desired electrical properties. When we talk about combining capacitors, we mainly deal with two configurations, in series and in parallel. Each configuration affects the overall capacitance differently, and understanding this is key to designing effective circuits. In series, the reciprocal of the total capacitance equals the sum of the reciprocals of the individual capacitances. This setup is useful when we want a smaller overall capacitance or to increase the voltage rating. Conversely, in parallel, the total capacitance is simply the sum of all individual capacitances, which is handy when we need a larger capacitance. It's important to recognize that the choice of combination depends on the specific requirements of your circuit. For example, if you need to store more charge, parallel is usually the way to go. If you're looking to handle higher voltages, series might be better. This understanding of combining capacitors ties back to our overall theme of circuit design, knowing how to manipulate and optimize component configurations to meet our electrical goals. So, always consider what you need in terms of capacitance and voltage when deciding how to connect your capacitors. All right, let's talk about the energy stored in a capacitor. When a capacitor is charged, it holds electrical energy in an electric field between its plates. This stored energy depends on the amount of charge and the voltage across the plates. The key point here is that the energy is proportional to the square of the voltage, which means even small increases in voltage can significantly increase the energy stored. This concept is important because it highlights how capacitors can act as energy reservoirs in circuits, releasing energy when needed. Understanding this helps us grasp how capacitors contribute to the overall behavior of electronic systems, especially in timing and filtering applications. So, the energy stored in a capacitor is a fundamental aspect that ties into the broader theme of energy management in circuits. Let's take a closer look at the electric potential due to a special charge distribution. When dealing with charge distributions that are more complex than a single point charge, we often need to consider how the potential varies throughout space. In this case, the key idea is that the electric potential at a point depends on how the charges are arranged and their distances from that point. For certain distributions, we can simplify the calculations by using symmetry or by breaking down the distribution into smaller, manageable parts. One common approach involves using variables to represent different aspects of the distribution, such as charge density or position coordinates, which helps us set up the integral expressions for the potential. Remember, the potential due to a continuous charge distribution is obtained by integrating the contributions from all infinitesimal charge elements. This approach allows us to handle even very complex arrangements. Throughout this process, it's important to connect these calculations back to the overall theme of how electric fields and potentials behave in different configurations, giving us a deeper understanding of electrostatics in real-world scenarios. So, understanding the potential due to special charge distributions broadens our ability to analyze and predict electric phenomena beyond simple cases, which is essential in many practical applications. All right, now let's take a closer look at the Van de Graaff generator, which is the main component here. This device is capable of generating incredibly high potential differences, typically around 6 to 8 million volts. That's an enormous amount of electrical energy, and it's what makes the Van de Graaff generator so fascinating. If you look at the diagram, you'll notice a series of numbered components and symbols that work together to build up this high voltage. The core idea is that it uses a moving belt to transfer charge to a metal sphere, which then accumulates a large amount of charge. What's especially interesting is how efficient this setup is at creating such high voltages without a direct connection to a power source. It's all about charge accumulation and transfer. This capability is what allows scientists to simulate high-energy phenomena, conduct experiments in particle physics, and even explore electrical properties at extreme voltages. So, in essence, the Van de Graaff generator is a powerful tool for generating high potential differences, and understanding these components and their interactions helps us appreciate how it can produce such impressive electrical effects.